Hey guys, let's talk about torque and simple machines, part of our circular motion and gravitation unit here. Torque is one of the things that causes rotation. So earlier, I want us to remember a few things here. We talked about what uniform circular motion was. And so remember, that is just an object spinning, so like a wheel, Ferris wheel, or a satellite moving around the planet, okay? There's all those inward pointing things. So down here, I'm going to draw this circle real quick, right? If something is moving on this outside edge, it has a tangential velocity, and then it has these inward pointing acceleration vectors, and I'm going to put this basically on the same side here, and then the centripetal force here. So we have those inward pointing forces and acceleration, tangential the tangential speed at the edge there. So what we're talking about now is getting that wheel and actually rotating it. And so if you'll see in blue here, we're going to talk about how we get the whole thing here and get it to rotate. And once again, counterclockwise is going to be positive. So the thing that causes a rotation is a torque, okay? And so what we have, think about a door, okay? So this is from the bird's eye view pointing down. There's the hinge of the door, and there is the door itself. And we know to open and close the door, we have to push on it. When we push the door, it's going to rotate one way or the other about the axis of rotation, okay? And so the hinge on the door is that axis of rotation, okay? So when you push or pull on the door, there's some kind of perpendicular force that opens it. So for now, I'm going to draw this force. We're going to push it this way. That is the force that we're going to use, okay? So that force is going to cause a rotation. The lever arm is this piece right here. It is the distance away from the axis rotation to the force causing the rotation, okay? So that's going to lead us to the formula for torque, and so we'll write it down here. Torque, spelled like this, T-O-R-Q-U-E. So torque is going to be the symbol tau, it's a funny looking T, equals FD. We're going to call this sine theta, okay? So torque is basically a force times the lever arm or the distance between that, okay? So I want to go into that a little bit further. So here is my object. So here's the axis of rotation right here. And here is my door, for example, okay? And we figured out that only the perpendicular force can do any kind of rotating on it. So if I have a force directed like this at some angle, okay, once again, my lever arm is going to be the distance to the force, okay? The axis of rotation is still sitting right here. Here's my force. So what we're looking at is only this vertical piece here, and the way we draw that angle, it'll be that angle right in there. So it's that vertical piece. That's the only thing that causes rotation. So we can do a couple of demos on this too, but if I try to push the door this way, what's happening is that force is actually directed through the axis of rotation right here. So since it's directed through that axis of rotation, it will cause no rotation. So only the force that is perpendicular, that's why we use that sine piece, will cause any kind of rotation, okay? So we can throw a couple of numbers at it. So here's a diagram. You might have to pause it to write this down and everything. But we have two torques acting on an object here. And once again, there is a positive and negative torque, okay? And so what happens here is we're going to call counterclockwise, we're going to call that positive, okay? And so what's happening is force 1 here on the left is causing a rotation to go clockwise, okay? And this F2 is causing a rotation to go clockwise also. And so that's going to help us figure this out. So when we start analyzing this, we start using our torque formula. So we have torque equals force times distance. And so there's a net torque. We can say it like this, the net torque, or you could say the net torque like this. Either way, it's kind of saying the same things. It's basically torque 1 plus torque 2, right? Which is basically saying F1 D1 plus F2 D2, right? That's kind of how that works out there. So I'm going to say the net torque here, I'm just going to use the F1 D1 plus F2 D2. So if I take a look at this, both of these are going to provide a negative torque, right? Or a counterclockwise torque. And so how we're going to set that up is like this. And it's going to be negative 15 newtons. That's the force 1 times D1, 0.14. Plus the negative F2, which is 11, times its distance, which is 0.07 meters. So we get a net torque of about 2.87 or about 2.9 Newton meters. And so a Newton meter is a torque. I'm sorry, negative. This should be negative. So what that means is because that net torque is this way, this is going to be rotating, whatever this object is, it's going to be rotating in a clockwise direction. So that's how a lot of our problems are going to go. There's going to be some kind of torque, some kind of net torque. We're either going to know what's going on at the end, or we'll have to find out the pieces in the middle. So once again, torque is FD sine theta. The units are a Newton times a meter. What that sine theta thing means is only the perpendicular portion or part of the force can cause rotation. Okay, and so once again, if I have an object over here, if I rotate counterclockwise, that is positive. If I rotate, If I rotate counterclockwise, that is positive, and if I rotate clockwise, that is negative. That'll just keep our convention there like that. All right, if you have any questions, let me know. Thanks. Bye.